Okay. Hi, everyone. Okay, so we can start. Can you hear me? It looks like it, yeah. Okay, so now I hope you had a good Thanksgiving and weekend and all that. So we are ready to continue now. The last thing we did was this, the idea of limit and continuity. For functions of two variables, three variables, etc. Right? So for a function of two variables, for example, we define what it means for this xy going to x0, y0 equal to L. So we define what it means for the limit to exist and be equal to that. And also, I gave examples where we were supposed to show that limit does not exist. So there are two issues side by side. So existence of limit and non-existence of limit. So you have to come up with some interesting ideas to show that the limit does not exist. Or show limit does not exist. Right, so these are kind of issues that we have to face. That's for limit. And for continuity, we say f of x and y is continuous at x0, y0 belonging to domain of f, it should be in the domain, so a couple of things should happen, right? If, first of all, the function should be defined at x0, y0 to start with. If f of x0, y0 is defined, first of all, and second, a limit should exist and should be equal to that value, right? Limit of f of x and y as xy goes to x0, y0 exists and is equal to f of x0, y0. Okay. So I emphasized last time that for the limit, to talk about limit, the value of the function at x0, y0 is totally irrelevant for this person, right? So, so this is A, and this is topic B. So I'm saying that for A, note that we don't need the value of f at x0, y0 at all in order to talk about the limit, right? The value of f at x0, y0, I mean, is irrelevant. I mean, it could be defined, it could be not defined, anything. We don't care about that. We just care about the neighborhood of that point and how what happens as you know as you're approaching that point, if the limit exists or not, right? Okay, so these are the two basic concepts in this section. Of course, before that, we talked about domain of such functions, and there's some examples and things like that. But these are the two basic. Now, let me give you an example so that we can, that we can handle these questions at least. Any questions about these definitions? Okay, there are no questions there as well either. So, okay, so let me now give you the example. So here's example. Consider the function f of x and y equal to sine of x squared plus y squared over x squared plus y squared if x, y is different from 0, 0, and 2, I would say 0, sorry, if x, y is equal to 0, 0. So such a function is given, and I'm going to ask several questions about this function. First of all, A, find domain of f. B, at what points f is continuous? Okay, so this is the function of two variables, sine of x squared plus y squared over x squared plus y squared. And so if xy is different from 0, 0, which is the origin, and is 0 if xy is 0. So the question is, first of all, we have to find the domain of f, and also we have to identify those points where this function is continuous. And hence, points where the function is not continuous, right? Obviously, if you know one, you know the other. Okay, so now the answer for the first one. So solutions. So part A. Can you tell me the answer to part A? Yes. X and y could be all real numbers. In other words, that point can be everywhere in the plane, right? Exactly, yeah. So domain of f is equal to R2. It's kind of chic to write R2 instead of saying all points. You can show off your knowledge of R. Yeah.
What is a range? What's the range when you're working with a function of two variables?
The range is the set of all values that are obtained by that function. It's the opposite of the domain.
Yes.
So it's like, since you asked, so this is domain, this is range, and this is the rule that takes you from any point here to any point here. Right? All these possible values is the range of this function f. I mean, this is the mental picture we should have. Now, if you're asking what is the range of this function, we can discuss that for sure. It's not so trivial, but we can discuss it.
So you can't write like y is an element of R such that anymore because the range doesn't only depend on what values y takes.
No, it's two values, so it's a bit more involved in this case because it's going from R2 to R. But in this case, I can tell you after we do this problem. Yeah. Okay. Cool. So domain is R2, which is the set of all x and y such that. Yeah, it's just the set of all x and y. X belongs to R, y belongs to R. So this is the whole plane. So the domain is everything, right? This function is defined everywhere. I mean, there's nothing that's not defined about this function. This is defined everywhere. Now, part B. what can we do about part B? So for part B, we are asked at what points f is continuous. So we have to find, first of all, at what points the limit exists. And second of all, at what points the limit is equal to the value of the function at that point. Okay, so let's go one by one. So we have to find the limit of this function. So limit of, so this is part B, limit of f of xy as xy goes to x0, y0. Now, it's a good idea in this case to divide this problem in or your solution into two parts. First of all, point is 0, or I mean is the origin, or if you're away from the origin, right? So let's assume that this is different from 0, 0, right? If this point is different from 0, 0, so you're here. So you're not at this point. So when you look at this function, you notice that the only interesting point about this problem is the origin. And everywhere else, this function is a tame, nicely behaved function. You're not dividing by anything like 0, right? You're dividing by some positive number, which remains positive if you approach that point. And this is also a nice function. There's nothing wrong with that. So the limit exists by the thing that it's a quotient of two functions. Limit of top and limit of denominator exists, so everything exists. So this is equal to f of x0, y0. So exists. And I don't expect you to prove this because I said for polynomial, for rational function, for reasonable functions, as long as you're away from the zeros of the denominator, you're okay. I don't expect you to prove that. Right? So that's fine. Okay, so what did we prove so far? What did we do so far? We showed that this function is continuous, at least at all points away from the origin, because the limit exists and the limit is equal to the value of the function at that point. So that's what we did, right? Okay. Now let's look at the more interesting point, which is 0, 0. So now we want to look at this limit of sine of x squared plus y squared, sorry, over x squared plus y squared as xy goes to 0, 0. Now, the question now is, does this limit exist? Right. So that's the question. Does it exist, first of all? And if it exists, is it equal to 0 or not? That's the question. So we divide our problem in two parts. Does the limit exist? It's a kind of tricky problem because as you approach the origin, this is getting closer and closer to 0 because x squared plus y squared gets smaller and smaller, and then the sine gets smaller and smaller. But this one also gets smaller and smaller. So you are like in a situation like 0 over 0 or something like that, right? So it's a bit tricky. So does the limit exist?
Can you do L'Hopital if it's 0, 0?
Well, yeah, you see, now it's a very good comment. I'm glad you made that comment. L'Hopital is for one variable functions. These are two variable functions. So we have to be careful about L'Hopital. I mean, we cannot just apply it carelessly, right? Because it's about two variable functions, but it's one variable function. So I would say right now, no. But if you can kind of massage this problem and turn it into a one variable question eventually, then you can use L'Hopital.
Can I use R to denote x squared plus y squared, and then there's a one function?
Then we can, okay, so there was a comment. Let me just read the comment. X equal to 0, there is, okay, yes, sine of x equal to x at 0. The sign is 0, but we have to be, okay. You see, the question is, we want to know if this really the quotient approaches somewhere, but you can approach 0, 0 from any direction. You don't just approach it from this direction or that direction. You're allowed to approach any which way you want. You can go even round and round and round. As long as we get closer and closer, you're okay. I mean, you have to also consider that possibility, right? But as it was said, we can do the following. Let x squared plus y squared. Well, I mean, this is the square of the distance, right? So let's call it r squared. Then you can write this as sine of r squared over r squared, right? This function is really sine of r squared over r squared. Now, we are looking at limit of sine of r squared over r squared as r goes to where? Approaches to what?
0.
0, yeah, exactly. It approaches to 0 because x and y are both approaching to 0, hence r is approaching to 0. So this is like a situation sine of r squared over r squared as r goes to 0. So now this is a kind of lucky situation. We have managed to turn this two-variable problem into a one-variable problem. Now you can use your L'Hopital if you want, or you can just look at it and say what the limit is, right? Can you just by looking at it, by gazing at it? Yes, it's 1. Why is it 1? Yeah, I know you're kind of complaining. Yeah, I know, or questioning. Why is it 1? Indeed.
I don't know, I just remember it from single variable calculus.
Yeah, but perhaps in single variable calculus, you had a rule, which is you're referring to that lim of sine of x over x as x goes to 0 is equal to 1. Yeah, that's absolutely correct, and you're allowed to use that. But someone might say, hey, this is sine of r squared over r squared. But it doesn't matter. Call r squared x. Give it a new name, or x, and this is a completely legit move. I mean, you can just give it a new name, because as r goes to 0, this x goes to 0, then this is like, okay, so either by appealing to this one variable calculus, or by appealing to L'Hopital rule again for one variable calculus, you can also prove this, because you take the derivative of this, and you get. Anyhow, this is 1. So far, we discovered that the limit of this guy as this goes to 0 is equal to 1. It's not a completely trivial problem. You have to argue, you have to kind of negotiate with the problem, right? Okay, now, is it continuous at 1? At 0, 0 now? No, because I was given the value is 0. But we found that the limit is 1. So the limit exists, but the function is not continuous at 0. Okay, so I can just say, so limit at 0, 0 exists, but f is not continuous at 0, 0. Because the value of the limit, which is 1, since 1 is different from 0. because 1 is different from 0, so it's not. Any questions about this problem? Yes, question.
So how do you write the answer? Because you have to find at what point is that continuous?
Yeah.
What's the format?
Well, the format is you just write down that this function is continuous at all points xy in R2.
Except 0, 0.
No, so continuous or defined. Did I say defined or continuous?
I meant continuous.
Oh, continuous, yeah, this function is continuous at all points different from 0, 0. Yeah, so let me write it for you, right? So if you want to write like a legal document, so that no one can complain later on, is this. So f of x and y is continuous at points x and y different from 0, 0. So points different from 0, 0, and well, this means and is discontinuous. If you want to be really, really rigorous, and is discontinuous. You could say it's continuous only at points such that, or we can just write it like this, and is discontinuous at 0, 0. But the limit exists everywhere. That's what we checked. The limit exists everywhere. I mean, this is a situation where you see like a limit is equal to 1, but the value here is 0. So you see, this function is approaching 1 as you approach the origin, but its value at that point somehow mischievously is given to be 0, not 1. So we are good. Any other comments or questions about this? Okay, so let's do another problem along these lines. So here's an example. Consider the function. F of x and y, comma y equal to, I believe it's x2 minus xy, yeah. x2 minus xy over root x minus root y. Okay, so the first question is find a defined domain of F. Of F. Sometimes maybe in your book even people write dome F. Something like that. Domain of F. And B is does limit of fxy, xy go to 0, 0 exists. C is find limit of f of xy as xy go to 0, 2. Okay. Okay. All right, so there are three questions asked. I mean, the first one obviously should be the first one. We have to know where this function is defined to start with, right? For any function, really, the first thing you want to know is the domain of the function to make sure that you know where it's defined, that you can take the values and all that. So that's a very reasonable question to ask first. So solution, let's look at A. So can you tell me what is the domain of this function? Yeah.
Everywhere where absolute of x doesn't equal absolute of y.
Oh, really? Okay, so it's
I would say also epsilon has to be greater than 0.
x should be greater than 0, y greater than 0, and
X doesn't equal Y.
x is not equal to y, exactly. Yeah. So first of all, I mean, for root x and root y to make sense, we need x different positive and y positive. And this is in the denominator, so they cannot be really 0. So it means that x should be different from y in order for root x to be different from root y. Right? So first of all, x positive, y positive, and I want that x different from y. Okay, so then let's look at the situation. I mean, this is kind of an interesting situation here. This is the line, the bisector of the first quadrant. This is bisector. And we are saying that we have to be x strictly positive, y strictly positive, kind of. But then the origin is deleted, and this whole line is also deleted. So it's like we are in this part, or we can be in this part. Otherwise, we are okay. Yes.
Couldn't like either x or y be 0 if the other one isn't?
That's also possible, yes. So for example, indeed, that's a very good point. I was thinking about it, but I was going to bypass that one. So indeed, x could be positive, but y could be 0. And then the denominator is absolutely okay. So in other words, we're saying this line is also okay. So let me just, so these are the bad points, and then this origin also bad, but this line is okay, and this line is also okay. So x positive or x equal to 0, which is this line, y positive, or y equal to 0, x positive, right? So this is x, this is y. So this whole line is okay. The origin is no, this line is no, this line is okay, and these two pieces are okay. Okay, so this was an excellent point. Yeah, very good. All right, so we have a good idea of the domain of this function. Oh, there are some comments. I noticed some of my colleagues actually have a TA reading the chats for them. Do you have this in your class? I should have that luxury. Why I don't have that luxury? Why I just making myself suffer all the time? I don't know why. I'm gonna get the chat reader, chat attender, right? Or yeah, that's right. Yeah. This is now done, right? Exactly. Should it be x positive and y positive? Can x equal to 0, y equal to 0, and x does not? No, well, if x is equal to 0, y equal to 0, then you cannot say x cannot be equal to y then, because you assign value 0 to both of them. So, okay, I think I got good comments also from group. Okay, so that's essentially, we have a good idea. Now let's look at this B. Now we want to look at limit of, so limit of x2 minus xy over root x minus root y, xy, go to 0, 0. I mean, obviously, because you cannot be on this line, you can't be on this line. Right? So you're going to 0, 0, but either through this route or through routes from top. Or this route is okay, this route is no matter how, but you can get closer to 0 by being any of those places. And so the question is, what is this? Can you give me what is the limit? Can you calculate the limit in this case for me? Why? Oh, you did the calculation. Okay. Okay. I want others to do that. Just do. So how would you find the limit? Yeah, that's right. So yeah, Ben also, yeah, this is already, if you look at this case, these things already, or something. Okay, so what is the limit? I mean, we have to do something about this question. I mean, we cannot just by looking at it find the limit. We have to, so in fact, we can just write it like this, x2 minus xy over root x minus root y is equal to, I can just factorize x times x minus y, and then I can multiply by root x plus root y, so I get root x plus root y. And then this is root x minus root y times root x plus root y. Okay, now, so this is okay now because this I can write as x minus y, and this cancels. So the whole thing becomes x times root x plus root y. So that's equal to x times root x plus root y over 1. There is nothing in the denominator, it's just 1. And what is the limit of this as xy goes to 0, 0? What is that limit? It's 0 because this is going to 0, this is going. So in fact, it's going rather strongly to 0. So this is 0. So part C was lim of this guy, x2 minus xy over root x minus root y as xy is approaching to, what was it that it was approaching to? Sorry, 0, 2. And notice 0, 2 is here. Indeed, we need this function to be defined in order to take. So we are coming to this point from different directions. And what is this value? 0. It's x is equal to 0. Why is it 0?
Because the denominator will go to negative root 2, but then the numerator is going to go to 0.
Yeah, so we can, so in other words, what we can do at this point, because it's not a point of singularity, it's not the point where the denominator is 0, we can just evaluate this function like that. There's no problem with evaluating it just like that. We can just sub in, right? That's the point. Just sub in, and if you sub in, so this is equal to f at 0, 2, which is what? Well, here is 0 divided by minus root 2, which is of course, so it's,
Can Can you actually plot these?
Oh yeah, no. This I discussed a little bit last time. These are, when you approach those points, it's very complicated, especially near singularities. So my best bet right now is to use Maple or Mathematica or just any of these free softwares online to get a profile of these things. I mean, I can plot them, but it's not worth the time spent on plotting this. But this is a good idea. You just do it for yourself at home leisurely and see, especially near singular points, these functions behave very strangely. Go up and down. It's very, very hard to figure out what's going on. Okay, so I'm gonna get a chat reader for sure. For C, could use the factor form from B. You can also, yeah, you can also use the factor form, or you can just directly evaluate at that point as well. Both works, right? Right. Great. Now we are going to go to a new section, which is partial derivatives. So I think we did cover good amount. So any questions about this limit and continuity in this section? Okay, so there are a lot of interesting questions in this section in your book. So actually, some of them are taken from there. So you learn a lot trying those problems. Actually, all of them are solved. I mean, somewhere you can check your solution. So partial derivatives. I believe this is section 4.3. I guess, not 100% sure. This is partial derivatives. Is it 4.3 partial derivatives? Can you verify? No. Well, whatever it is, it is what it is. Partial derivative, that's the most important thing. So, remember the derivative of a function was defined. So one variable case. So let me recall definition of derivative to start with. I mean, from one variable case. Well, of course, I mean, this was defined, if the limit exists, this was defined to be lim of f of x plus h minus f of x divided by h as h goes to 0. Right? So this is, yeah. If it exists, then we say, yeah, this is partial. This is the derivative of function at that point. Okay, of course, geometrically, we know what it means. It really measures the slope of the line, tangent line, and all that. Now, if you have a two-variable case, which is today, function. So you have a two-variable function, f of x and y. And now, you can take derivative with respect to x or with respect to y. You have two choices because you have two variables to play with, right? So definition is the f partial x, right? And yeah, at some point x0, y0 is equal to limit of f of x0 plus h, y0 minus f of x0, y0 divided by h as h goes to 0. So you notice that, I mean, this is kind of copied from this original definition of one variable case. except that because we have two variables, so either we take derivative with respect to the first one or with respect to the second. Okay? So if this limit exists, this is called the partial derivative of f with respect to x at x0, y0. This is partial derivative. Partial derivative of f with respect to, I just write WRT, I hope it's okay, with respect to x at x0, y0. Okay, so that's the thing. And we can also take a partial derivative with respect to y. df dy at x0, y0 is equal to limit of f of x0, y0 plus h minus f of x0, y0 divided by h again as h goes. So what is it that we are doing here? So we are looking at this point x0, y0, and we are looking at, yeah, this is the point x0, y0. So in first case, we are approaching it along this line. And in the second case, we are approaching this point along this line, right? Because these are the points x0 and y0 plus h. And this is the point x0 plus h and y0. And this is the point x0, y0 plus h. That's it. So we are looking at the difference quotient along this line and difference quotient along this line. And if the limit exists, this is called partial derivative. Okay, so notationally, this is one notation, but there are different notations. So there is an alternative notation we use all the time. So we just say f sub x. It's called f sub x, partial derivative with respect to x, which is the same as df dx. Now I'm trying to remember if there is any other notation we are using for partial derivatives. I don't think so. Well, at least I don't remember right now. After 40 years. More than that. 50 years. Almost 50 years, yeah. Okay, so yeah, there we go. F sub x equal to partial derivative of this. Okay, so and then of course partial f sub y is equal to partial f with respect to y. So now, yes.
Another notation, if it's the second partial derivative of x with respect to, or partial derivative of f with respect to x.
Oh, the second one.
Yeah, would that be f sub xx?
Of course. This will come a little later. Yeah, in the next section maybe. Yeah. Still, we have to do. I have to give you some examples now. I will give you some examples now. Okay. All right. So, okay. So now, how we are going to calculate this? Basically, You don't need any new toolbox to calculate these partial derivatives. What you know from one variable case, if you apply your knowledge carefully, that's enough. So let me give you an example of computing partial derivatives. I mean, it's just common sense. So here is an example. Find f sub x if f of xy is equal to sine of, say, x squared plus y squared. For example, what is that partial derivative with respect to x? What would be that? Okay, so we have to go back to the definition. What does this definition is telling us? The definition tells us that to compute partial derivatives, we have to consider we have to freeze the other variable. We have to consider that the other variable is not changing as a constant. The other variable should just be a constant, that's it. So, so we have to treat, so solution is this. Definition implies we have to treat y as a constant. That's exactly what the definition tells us, right? As a constant. Okay, so if we treat f as a constant, what can you say? What can you, yes?
Sine of x squared plus y squared multiplied by 2x.
Exactly. It's just like 5. Then what would be the derivative of sine of x squared plus y? Well, of course, it would be 2x cosine of x squared plus 5. So this implies that f sub x is equal to 2x. So let me write it like this: 2x times cosine of x squared plus y squared. So all you have to do, you have to be careful to treat one variable constant as constant, the other variable as your variable, and vice versa. And otherwise, everything works. So you want to do so here's another example. Find of y, so that's good. I'm done. If f of x and y is equal to e to the sine of log of, so ln of xy. Just for fun. So what would be f sub y?
E to the sine ln xy squared times cos ln xy squared times 1 over xy squared times 2
Yeah.
xy.
Yeah, I believe so. Now, yeah, that's the idea. But I'm going to teach you a method that you will never, if you follow that, you will never ever make a mistake. So that method is like this. You don't have to, put pressure on your brain to write this first. Just you ask yourself, what was e to the u prime? What was it? You remember the derivative of e to the u using chain rule or something, which is u prime e to the u, right? It's just u prime e to the u, that's all. Okay, so in this case, then, so fy, you just say, okay, fy is equal to, you have to take the derivative of this guy with respect to x, sine of log of xy squared So I put here with respect to x times e to the sine of log of xy squared. Okay? So all you have to do is to compute this. That would be your first line. So that's exactly like how a computer would compute this. And it's better to be like a computer here. Don't be too creative with these problems. Just be mechanical. Okay, so we have that, right? So now what's the next line? So the next line is, again, you want to know what is sine of some function derivative, right? So, well, then this is equal to sine of u prime is u prime cosine of u. So it's just ln of xy squared. Oh, I'm doing y, by the way. Ln of xy squared with respect to y times cosine of this. Cosine of ln of xy squared, right? Times e to the sine of e to the sine of ln of xy squared. All right. Okay, now the last step. So what's the last step now? The last step is like we have got ln of something, again, like ln of u prime. What is the derivative of ln of u? It's u prime over u, right? So this is equal to xy squared with respect to y divided by xy squared. And then the rest is cosine of log of or ln of xy squared times exponential of sine of ln of xy squared. Okay, now this you can easily compute, right? This is equal to what? What is the derivative of xy squared with respect to y? Well, it's just 2xy. So it's just 2xy divided by xy squared. And there is some simplification. This goes with that, that goes with that. So it's 2 over y squared, sorry, 2 over y times cosine of this function times e. So I gave you a hard problem to start with because other ones are kind of boring, but that's the idea. You have to be very systematic. Use what you know from one variable calculus in a systematic way. Write all the steps, and then there's no way you can make mistakes. Okay, guys. So now I have to go and ask our marker grader to grade your assignments. Okay. Have a wonderful day. Any questions, by the way? Okay. Thank you all. Thank you. That's okay. I'm going to look into that. Don't worry about that. Yeah. You, yeah, I will help you. Don't worry. Yeah, that's okay. That's okay. I'm talking to Hadi, so that's fine. Others also, everything is okay. So that's good. Yeah. Wonderful. Very good. So I just stop the video.